So now we'll have a look at data analysis, an introduction to data analysis, what a data analysis or workflow looks like. And I'll also give you a detailed example or a case study of data analysis, some data from wind from Eastfjorden. Okay. So we'll start again. We'll start again with what is data analysis. We'll look at the workflow of a data analysis. We'll look at the types of data. We'll look at what is one of the most important steps in data analysis, that is pre-processing. And then we'll do some exploratory data analysis and then some goal-oriented data analysis. Okay, so what is data analysis? Well, it's basically you analyze some data. We do it all the time. We look at some things around us and we are analyzing data constantly, right? But what we are going to talk about is something more systematic. You collect some data and you do it in many ways. Then you pre-process that data, you clean it, you format it in a way that is useful to others. And then you analyze the data by visualizing it or modeling it in some way. And then you present it to make it useful to others so that the conclusions can be supported by whatever you found in the data. And then you use those conclusions to drive policy or drive some kind of decisions, right? Data in and of itself is very limited in its usefulness, in the sense that you can have lots of data but do nothing with that data unless you can make some conclusions based on that, right? So the conclusions are what are important. Data is something that it is important, but it's not useful in and of itself, right? So let's start with data collection. People collect data all the time. We collect data from ships. You collect data from drones. You collect some data from the AUVs. So this is from one of our fieldwork trips, and we are deploying some AUVs in the water, and that would collect some CTD profiles and some side scan sonar images. And that's also one way of collecting underwater data. You collect data on land. Researchers go, they walk and they collect data of glaciers, they collect data of vegetation, soil samples and other things. You have weather stations that collect data about wind, other things. And then you have remotely sensed data from satellites, which collects our images, sometimes optical images as well. You have two different main types of data. One is structured data, where you have a very defined structure of the data. You have some, and all points in your data, they have this particular defined structure, right? So you have some kind, it mostly looks like a table where you have some different columns, and all of those columns, these columns represent something. So latitude represents latitude, because longitude represents longitude. Then you have conductivity. So this is a CTD measurement from Templefjorden, and we were trying to find the conductivity, temperature, and density. So this is a structured data. You know what you're looking for. You know that for each point, you'll have some conductivity, some temperature, some salinity, some depth. There's wind data. This is also a structured form of data. So you have different columns. You know, for every year, month, date, hour, you have some wind speed, you have some wind direction, you have some wave height, some time period of the wave, and mean direction of the wave, right? Then you have unstructured data. Unstructured data is something that has no defined structure, as to say. For example, a sentence, right? So if you speak, you don't always speak in a particular manner. There's no template to how you speak. It's very unstructured, right? And it varies over languages. So if you are speaking French, it looks very different. And one person speaking French will speak it in a very different way from another one, right? So you can't have strict rules, so to say. Then you have images. These images could be of anything, right? They can have cars, they can have whales, they can have polar bears, or they can have vegetation and a lake in it, right? So there's no defined structure in this image. You don't really know that this part will represent something or not, if there will be something in this part or not, right? And it varies over images, it varies over data sets, it varies based on where the drone image comes from. As compared to this, let's say it doesn't matter which weather station you use, you'll get a particular value here that will be an integer and it will be within certain limits, right? You can't say the same about an image. Then you have audio data. This is also not structured. It's just signal that can have a defined amplitude, but how the amplitude will vary is not well defined. So we have two different kinds of data. One is structured and one is unstructured, and you analyze them a bit differently. We will look at both now. Then you have semi-structured data. So semi-structured data looks something like this. You have some unstructured data, let's say an image, and then you have some structure. So this is metadata about this unstructured data. So you have an image, let's say, and then you have some geotags. So where was this image taken? And that will be a latitude and a longitude and some time, right? Then again, you have some temperature and wind data from this particular place, let's say. And you know that the temperature will be in Celsius or Kelvin or Fahrenheit. You know that the wind data will be a velocity, right? So this is structured data. This is unstructured data. You combine them both. They give you some different, they tell you different things, but they can be put together. And that's when you call it semi-structured data. Then we move on to cleaning. Data, whenever, doesn't matter if it's structured or unstructured, it's just best to assume that it's going to be dirty, especially if it is manually entered. So what you see here is the ship reports from the Northern Sea route that I showed you in the last slide, in the last presentation. And you have the name of the vessel that is going, it's a ship that is going somewhere, and it has to report to this particular administration, but with the positions, with the speed, with the heading, and where they're going, or the ETA to where they're going, right? The problem is this data is manually entered, right? So you might have the IMO numbers are correct all the time, but the latitude and longitude, you see that it depends on the operator. Sometimes they enter 7200, sometimes they enter 72 point something, sometimes they enter something else, right? And it's not very consistent across rows. So this is a prime example of what real world data looks like. And it's very dirty. And then you don't really know how they have entered. So for example, some people start with 08. Someone else would write 8, directly 8. You wouldn't add the leading zeros, right? Yeah, some people use commas for as a decimal. Some people use like dots. So it varies over time, and it varies with person to person, and that's how you get noisy data, right? Some people write, okay, so this is from the Russian website. Some people write the name, the ETA in English. Some do in Russian. So you need to know that, okay, your data is going to be very dirty. You need to pre-process your data before it is useful for anything. Sometimes you have inconsistent formatting in the data, right? For example, some people might write this the other way around. And I've seen that in this data. Of course, you also have missing information. Sometimes you miss the headings, or sometimes you have a zero speed or something else. And that also you need to take care of before you analyze your data. Then we come to processing the data. You have data in different formats. So for example, here you have a vector map where you have these polygons on a map and they represent something. In this case, it is a CI chart where each polygon represents a particular area, and that particular area has some CI's concentration. Right? Now, this I chart is in a vector format. That means these are polygons and they are defined by the boundary. What if I wanted this data to look something like this? This is the rasterized format of the same data, right? So these polygons, I rasterize them and they look like these now. So now in this particular format, the data is every point has some value. In this case, it wasn't like that. It was defined by its boundaries. This is useful for something. This is useful for something else. But if you want data like this, then you have to pre-process your data. Then labeling of data. It's very important because if you want to, let's say, train some neural networks or any machine learning model, you need to label your data, right? Then combining data from multiple sources. So let's say you have some optical images, you have some data from satellite images. How do you combine them? You need to think about that as well. Okay. Now resizing and cropping. This is more related to image data. Sometimes you collect images on the internet. For my data set, what we did was we just found, we went on the internet on different search engines, typed some keywords, found all the images that we could, and downloaded all of them. Now, all of those images were taken from different cameras at different times, in different angles. They had different resolutions. But when you're training a neural network, you want all the images to be of the same kind of resolution, right? So you need to analyze what you get, what the data we had, and then we resized and cropped them so we could get something like this, with a more uniform resolution of the images. It's not as simple as just resizing and every image, because you see some images are taken from, let's say, ships. Some images were taken on the ice. So how do you also need to ensure that when you resize the images, you keep the resolution same, the spatial resolution inside the image same. So it's a bit more complicated than just resizing. Then labeling. Okay, you have some images now. What you want to use these images for something? Let's say you want to predict if there is low vegetation or high vegetation in the image. So you need to label these images. For example, this image has very little greenery. This image has more greenery, but you need to label it first so that the neural network or the model that you're trying to train knows that. If you were trying to predict something else, let's say there's no water in this one. I can see some water here, and you can see some land and some grass. So these are labels that you can give to your data. And I would say this is the most important part of your data set. This is where the value lies. You can create multiple neural networks. You can do whatever you want. If you don't have the right data, you have nothing. Again, labeling the data. So now we had images. We wanted something like this from the neural network. We had to label it ourselves. I did this labeling. It took me 20-30 minutes per image. I did it for 400 images. It took me 2 months to do that. And it involved basically, okay, you have an ice feature. You want something like this, you create a polygon around this ice feature. You create another polygon around the different ice feature. And you can do the same segmentation labeling for all kinds of segmentation applications, right? There are labeling tools that are available online that you can use. These are very efficient. They also provide you the option to ask someone else to label it for you. So the link at the bottom, this is a GitHub link, and you have a list of all nicely curated data labeling tools. Some of them are open source, some of them are paid. But if you want to label, and they have different kinds of data, so you can use some tools for images, some tools for labeling text, some tools for labeling some other kind of data. You can have a look at this list if you want. It's very useful.
Your presentation will be shared with us?
It's recorded, and I will send you the link, yes, of course. And of course, the presentation as well. Okay, now how do you combine data from multiple sources? You see that, okay, you have an image from a car, let's say. You have some view from Google Maps. You know that these two data sets are completely different formats. This is an image. That's probably a vector data format. You need to find a common ground, and you need to combine these two data sets. Let's say this one has some metadata about the location, and you know the location here. You need to combine them, right? So this involves some intricacies, and you need to know how to deal with this data, right? And that's where the crux of the entire thing lies. Okay, now you have, let's say, the same image that we have been looking at. Then you have some temperature and wind data or other variables, let's say reindeer population or something. You can combine them too as well. Yeah, let's move on to some data analysis now. So there are two main kinds of data analysis, at least in my view. The first one would be the exploratory data analysis. So that's where you try to understand the data that you have. And how do you do that? You ask some questions about your data. Let's say, what is available to me? What do the variables mean that are available to me? How are they formatted? Is it consistent? What are the range of values? Is there any error in my data? Are some values missing? Are there formatting errors? And you answer these questions using some visualizations and some data manipulation. And at the end, you refine the questions. Okay, so now you have answered these questions, you have cleaned your data. Now you define your questions for further analysis. Let's say, okay, I have some data and I want to understand the variations between two particular variables, right? You can refine that question by using information that you found here. Let's say you can also ask question about the temporal and spatial coverage if you have geotag data. You do this, and then what you get out of it, you use that for goal-oriented analysis. And that involves lots of manipulation of data, lots of coding. And then you can also model your data here. And you visualize what you get out of the model. Yeah, this is an example that we will look at in detail today. So say I want to conduct an operation. So outside of East Fjorden, I want to install something there, and I have the wind data for that particular area. How do I use that data to make a decision? So to begin with, my data that I got, it looks something like this. It's a text file, .dat format. I don't know what .dat format was until I looked at this data. I still don't know what it is. I saw that, okay, there are some lines of text at the top. Then my data starts from here. So what I want is just particular this thing. Then you read that data in Python. You won't always have a particular library to read this into, right? You can use pandas sometimes. You cannot use pandas sometimes. So you need to be able to write your own code to read this data in Python or R or whatever programming language that you're using. Then, okay, I was like, okay, what are these variables? They're just short forms of some things. So I see, okay, I get this, they are defined here. So WS, that is the wind speed, it is in meters. WD is the wind direction, it is 0 at the north, it is from the north. And then you have the height, wave height, so the height of the waves in East Fjorden. And then you have the time period of the wave, and then you have the mean direction of the waves, where they're flowing. Then I looked at, okay, I have some variables. I don't know what this data should be in the range of. So I wanted to see how these variables are formatted, or what are the values in those variables. So like, okay, give me the minimum, the maximum, and the coverage of the data. So you see that the years, it starts on 1957, goes till 2021. Month starts from 1 to 12. That makes sense. It shouldn't be out of this range. The days, it starts from 1, go to 31. That's also fine. The hours, they start from 0, go to 21. That's also okay. Wave wind speed. This also seems fine. It's 0.1 meters per second to 27. That's a bit high, but you do have sometimes high speeds outside there. In some cases, you have things like, okay, -1. Now, the wave height cannot be -1 because you measure it from the mean sea level, and you always measure it on you measure the wave height it's always positive, but I see that there are some negative wave heights here. That shouldn't be the case, like and that was because they didn't record the data for some particular duration. That's why you have -1 values. And I must admit, when I was analyzing this data, I completely missed these three things. I just didn't look at this particular range distribution. I just did my analysis. Towards the end, someone else was doing the same analysis. He told me, well, why are the minus values in your in the wind data? And I was surprised. I went back to look, and I was like, oh, there are so many negative values. Shouldn't have missed. So I would advise you, if you are looking at some data, please look at the range of variables and make sure that it makes sense to you. Okay. So now, then you clean the data. You remove the values that are not useful. So the -1 values, I removed all of them. But I wanted to know, okay, where are these missing values? Are they in 2010 or 2020, or were they from 1957? So you see that the missing values, they are mostly towards the start of the data. So 1957 to 1980s, and later on you have less missing values. So it also helps to understand whether your data is missing, right? Now, in this case, I don't care much because I know that the most recent data is the more complete one. So it's okay with me. Here you see a wind rose. So I wanted to find, okay, what is the mean, the most dominant direction of wind? Turns out it is between 90 to 135 degrees. You can also look at the distribution of your main variable. Here my main variable was the wind speed. I wanted to see how, is there any significant variation if you go from 1950s to let's say 2020? Well, there isn't so much. You can see that it's mostly uniform. Okay, then the waves in oceans, they are created by wind and sustained by gravity. So if you have high winds, you should expect high waves, and they should be correlated. You can almost write an equation from wind speed to wave height, and that should reflect in the data, is what I was expecting. And I wanted to see if it does. So I plotted the wind wave height with respect to wind speed, and you see that there is a proper covariance, high correlation between the two. You see when the wave height, when the wind speed goes up, the wave height goes up, and that's what you would expect. Then I was like, oh, I have colored these wind speed by wind direction, and I see that there are some yellow thingies here, and they seem to be in a particular pattern. I wanted to find out, well, is the wind direction dependent on the wind speed? So I plotted wind speed against wind direction, and you see that there is barely any pattern. The wind direction is, then maybe you can say that, okay, when the wind direction is around 100, you see higher winds, especially the highest winds are from the east, right? And now they are colored according to the months. The idea here is that you visualize your data in different ways to extract different kinds of information, right? And this is an example of how to do that. Then I was like, oh, does the wind speed depend on month? It should, because you see a lot more wind in winter and you see less wind in the summer. So you plot wind speed versus month, and then you see, okay, there is high winds in December, January. This is weird. It shouldn't be like this, but okay. You see high wind in December and January and February, and low in June and July. That is kind of the summer, and August. Okay. Now we come back to our question again. The question was, if I want to conduct an operation, what I want is, I want the wind speed to be low enough, and I want the waves to be low enough, and I want that to happen for long enough to be able to operate there, right? So I was trying to find, okay, there are three categories of wind speed. Wind speed, first one is 0 to 10 meters per second, 10 to 25 meters per second, and more than 25 meters per second. So what you see is that in January, February, March, and April, you see some wind that is very high. And in the summer, you see that the wind from 0 to 10 meters is much, takes up, most of the time, the wind is low. That's okay. Then you calculate the average calm period. Average calm period is basically the length of the duration for which, let's say, the wave height is lower than some value. And then you would expect that if you consider a higher wave height, let's say 3 meters per second, you would expect it to be calmer for long. And that's what you see here. And you can see the variations in the average calm lengths as well. And you see that over the summer, it varies more than over the winter. And based on these two things, I can make that decision. So, okay, so I want to install something which is going to take me a few hours, let's say 300 hours or something. Then I would do it in May, because that's the only time where I can have enough calm period, right? So this, you analyze your data, and then at the end you use that data to make some decisions. Okay, then we move on to other presentation. This is another example. We are analyzing sea ice charts now. Okay, so what are sea ice charts to begin with? Sea ice charts are basically vector charts where you have on a map, you get some kind of sea ice information. So in this one, you see that some part of this map is new ice, some part of it is gray ice, some part of it is gray white ice, some is medium first year ice, and so on and so forth. So these are provided to you by this particular chart comes from the Russian meteorological organizations. You have sea ice charts from the Norwegian Meteorological Organization. You have it from the National Ice Center in US, and you have Finnish Ice Center. You have the DMI from Denmark. They all give you these sea ice charts, and they illustrate ice conditions in a particular area. They are basically a set of polygons, and they give you information about the concentration, type, and partial concentrations. These ice charts, they're very useful in the Arctic when you are planning some particular operation. They're also useful when you're doing some climate change studies or you're validating satellite algorithms. What we wanted to find out, okay, you have sea ice charts from 5 different organizations. How do they compare to each other? They are supposed to represent the same thing at the same time, but do they report the same value? We were trying to analyze that. So what we did was we looked at sea ice charts from 3 different organizations. Yeah, the Met Norway, the Arctic and Antarctic Research Institute, the National Ice Center in the US. And then we asked some questions. Okay, how accurate is the sea ice chart that you're using? And how do you assess the uncertainty in sea ice charts, right? You do it by, so firstly, you understand where that uncertainty in your data comes from. In our case, it was from the procedures, because these organizations are from different countries, different people work there, they have different procedures. That's where the uncertainty in your data comes from, right? It could be that some people create sea ice charts differently than others. So let's say you have 2 doctors, they're reporting the same thing, but they have different experience, so they do it differently, right? That's an uncertainty in your data. The work culture is different. A data set made in India would look very different from a data set made in Norway, would look very different from a data set made in the US. So that's also a source of uncertainty. Input data. If you have good input data, you get better reports. If you have bad input data, well, bad outputs. For this study, what we are trying to do, okay, you have sea ice charts, you want to compare them. You have one sea ice chart from a particular organization. You have 3 different sea ice charts from 3 different organizations. And then you compare the total ice concentration reported by each one of them. And then you analyze that data to get the temporal variation of the sea ice charts. You also look at the spatial variation in the differences. The idea here is to see that, okay, you can analyze something and then you plot it with respect to time to get the temporal variation. You plot it to this on the map to get the spatial variation. You define for, okay, if you want to do some data analysis, you define an area of interest. So if you're doing some geospatial data analysis, you are doing that. So we defined an area of interest. This is basically a particular sea in the northern sea route, and we have sea ice charts for this particular sea. You have 2 different sea ice charts. You have sea ice charts from the Met Norway, and you have sea ice charts from Ari. Now, you have some data. You want to understand where that data comes from and how often it is reported. In our case, that data is from 2017 to 2019. It was reported 5 times a week. It provided us the ice type. So this data was reporting ice type in these 6 different categories. Then you have a sea ice chart from another organization, but they report completely different things. They report the stages of development of ice instead of the sea ice types. So we had to get them together in a similar format to compare. One more thing. You have these vector charts, right? So what you see, these boundaries, they are polygons. This is one sea ice chart. This is another sea ice chart. They come from different organizations and they have different polygons. How do you compare a polygon that looks like this to a polygon that looks completely different? So you need to get them in a similar format to compare. And that you do by rasterization. So you map this vector data to these rasterized data. Basically, convert the vectors into these point values. And then you compare each point with another point on the CI. Okay, now this involves some coding, because you need to know these. You need to know how to read these CI charts. You need to know how to process them to get them in a particular format where you can compare them, right? Now you calculate the differences between these CI charts. You have one CI chart where you have these pixelated values. You have another one in the same format. You subtract each one value from the corresponding value on the other chart. So you get something like this, where it's a difference between the two. Now you have these these comparisons for months, for 3 years. Let's say you have we had around 160 such charts. You can't have a look at 160 values one by one to find pattern. So what you do is you condense this data into something that is easier to understand, and you visualize that. That means looking at something like this. So you have the difference again, but now you put it on against time. And this is, of course, a bar chart where you and 3 different colors. They represent 3 different years. I wanted to see how it varies over years. For example, if the differences between ice charts was more in 2017, it was comparatively less in 2018, and then even lesser in 2019, right? Now you make some conclusions based on this data. So the conclusions that we made was, okay, you see that for most of the year, the differences are on the other side of zero. That is, the RE concentrations are reported more than the MET concentration. But for this part of the year, for the summer, there's no trend as such. You also see that the differences are higher here. They go down, then they go up, go down. That's also a trend that we reported. You also see that, okay, this goes down. So for 2017, it's higher, 2018 lower, and lower and lower. And it holds across the months. Then you have some spatial variations. Now you see here is a GIF. So it varies. It goes from August, September. Yeah, it's for the entire year, I think. And then you see the differences. So where it's yellow is it's where the differences are higher, right? So you see that the differences are moving over the map as you go from month to month. And you create these plots in Python. These plots were created in Python, and I might be, if we have time today, we can also look at how to create these kind of plots. Okay, how do you use all of this, whatever analysis that you did? How is this useful again? It's useful because you need CI charts for planning your operations. Now, you need to know if the uncertainty in your data impacts your decision. The plot that you see here is like, okay, when it's green, it means that the uncertainty in your data is not going to impact your decision. When it's red, it's going to, it is likely that it might impact your decision, right? So we had lots of CI charts. We had lots of CI charts from other organization. We compared all of them and condensed them to a particular format where it's just red and green, right? So you have yes or no from lots of data. And you get there by doing lots of manipulation and then analysis. You also need to understand the limitations of your work. In this work, it was like, okay, we will compare the CI charts. They report a range of concentrations, but we were only comparing the average. We know that there are more CI products. We were only comparing the two. We also know that we could not explain the differences, where the differences in CI charts were coming from. And there were more attributes. We were just comparing the total CI's concentration. We could have also compared the size of thickness of CI or something else, right? So you make some conclusions based on your data. You have some limitations that apply to these conclusions, and then you apply your work somewhere. And for example, this work was useful in operational planning. And it was also useful in uncertainty measures because people use these CI charts as inputs to their machine learning algorithms. You need to understand the uncertainty in your data. And so we were studying that for them.